Hi all. In the next 5 to 6 videos, we are going to see about turbulence, what is turbulence, and how to model the turbulence phenomena in a fluid flow. So to understand turbulence, we have to understand phenomena called bifurcations in a dynamical system. So since fluid dynamics, all flows are termed as dynamical systems modeled by Navier-Stokes equations. In a dimensionless form, this Navier-Stokes equation has a parameter called a Reynolds number, which is defined by UL by mu, where U is the characteristic velocity scale, and L is the characteristic length scale, and V is the kinematic viscosity. And this dynamical system, like a fluid flows at low value of this Reynolds number, they are highly stable, and the stable state is termed as a laminar states. But when it comes to a higher state, after a critical parameter of that, bifurcation occurs and it becomes a completely random and chaotic and unstable state. So that state is called as a turbulent regime. So the next 5 videos going to be based on these 5 sections of this book from this chapter number 3, turbulence and its modeling, from the book called CFD by Stick and Malasekara. So section 3.1 is going to describe about generality of the turbulent flow. 3 point is going to describe about the physics of the turbulent flow, how the transition happening from laminar flow to turbulence. Section 3 point is going to be about how those turbulence can be described by a time average Navier-Stokes equations, which is based on the phenomena that any flow quantity like a velocity can be decoupled as a mean quantity and a fluctuating quantity. Section 3.4 is going to describe about how that time average Navier-Stokes equation is different from the Navier-Stokes time dependent Navier-Stokes equations. How that extra terms appearing are termed as Reynolds stresses due to the velocity fluctuations. Section 3.5 is going to describe about how we are going to close this time average Navier-Stokes, because these extra terms, how we normally in a Navier-Stokes equation, the extra terms like stress tensors are closed by a constitutive relation similar to that setup. How these extra stresses due to that velocity fluctuations can be closed, and we are going to derive a closed form time average Navier-Stokes equations. So this video is going to be about the generality of the turbulence. As I mentioned earlier, it is based on the bifurcations occurring at the Navier-Stokes equations due to a parameter called a Reynolds number. The Reynolds number is, I mentioned earlier, is going to be UL by mu. So this is going to be the numerator is defined to be as like a convective term, and the denominator is going to be as a diffusive term. So more in another way, we can say the numerator is going to be defined an inertial term, and the denominator is going to be defined as a viscous term. How far the domination of the viscous term, how far the domination of the inertial term is going to determine the value of the Reynolds term. At higher value of the inertial term, the Reynolds number is going to be high, and if the viscous force is going to be dominated, the Reynolds number is going to be low. So when the viscous force are dominated, the Reynolds numbers are low, and it becomes a steady, like a kind of a smooth flow, and there will be some kind of a layers of fluid flow adjacent to each other, and they don't have much interaction between these layers, and this regime is called as laminar flow. But after a certain parameter, that bifurcation value, and this flow behavior doesn't exist, and it becomes somewhat like a random and chaotic, and because of the dominance of the inertial term, that numerator, it dominates the viscous terms. So this regime is called as turbulence. In this regime, there will be like kind of a fluctuation similar to like this, and where we can discretize, like decompose those instantaneous velocity term like a chaotic values into two things. One is mean value and the fluctuating values. The fluctuating takes all those chaotic nature. So the randomized part is been captured in this fluctuating part, and we have the mean flow. So though the mean flow is have not varying much, but it can have some kind of two-dimensional variations. But the fluctuation is always like of three-dimensional in spatial terms. So because of this fluctuation and this main flow things, there are particularly there is an interaction between the layers as related to the physics, and there can be a large of length scale between length scale of eddies. So particles, they have like kind of contributing to each other, and they exchange momentum and mass and also heat. So turbulent is some way, it is like kind of a good way of giving the things. There can be like kind of a large eddies to the small eddies. The large eddies are like kind of like more level interact with the kind of an angular like a large scale, and the small scale is going to be like kind of interactions with the same kind of a viscous scale. So the large scale, due to the fluid flow from one direction to other directions, what I can say, this it will be like kind of a stretching phenomena. Like in the flow directions, it will be more stretched, and in the opposite to the later perpendicular direction, there won't be much stretching. So this because of this effect, usually the large eddies are termed to be like a kind of an anisotropic in nature, but the small eddies are somewhat like it is related to some kind of energy. It's related to kind of an energy loss. The reason is the mean flow, or the large eddies interact with the mean flow, and it extracts the energy from the mean flow, and it transfers the energy to the different scales of the eddies. And finally the small eddies takes all those energies, and those energies are dissipated and converted into thermal internal energy. So this kind of energy transfer between large eddies to the small eddies of different length scales is the term to be like a kind of term called as an energy cascade. So this is all about the physics happening in the turbulent flow, especially the formation of eddies of different scale. That is the main characteristic of the turbulent flow, which does not happen during the laminar sections. Thank you. Hopefully, we'll see about the hydrodynamic instability, and what about the transit, why the transition happening to the turbulent flow in the next video. Thank you.